note that the Green's function, it doesn't depend on the source time t naught and the response time t. And source time t naught, that's an important idea. T naught is the source time, and t is the, well, it's the time in our solution, I guess. But you might, what's he point out here? The Green's function, what does it actually depend on? Oops. See this here? Well, it doesn't depend on t or t naught independently, does it? It depends on t minus t naught, right? Mm-hmm. So it depends on what he calls the elapsed time. He says this
isn't t naught was or was not a variable though? I mean, you said it was like a variable, but it was.
Well, he calls it the source time. He's thinking of the source. I guess the idea is you imagine the source doing whatever it does at time t naught. Then the question is, how does that affect the solution at time t? Mm-hmm. That's the concept. I mean, but what he says here is he says that the reason the Green's function just depends on the elapsed time is because the heat equation has coefficients that do not change in time, because the laws of thermal physics are not changing. It says Green's function exponentially decays in elapsed time, t minus t naught, yeah. So that means that the influence of the source at time t naught diminishes rapidly. It's only the most recent sources of thermal energy that are important at time t.
Yeah, makes sense.
Let's see here, what else he say? You can see the causality principle at play here. Integrate. We also integrate the sources over all past times. 0 less than t less than. I mean, t naught goes from 0 to t, right? See that? That's also apparent here, right? You see that what happens to the source at times greater than t doesn't matter. The the way the temperature behaves at time t is just due to the way the source behaved from time 0 to time t. Right, this t naught is going between time 0 and time t. So that's an important, I think, comment. Anyway, here's the question he asks to investigate later and for other problems. Are there more direct methods to obtain Green's function? Well, thanks. Better not find a more direct method after I went through this. Are there simpler expressions that we can... simpler expressions for it? Can we simplify this? Can we explain the relationships between the influence of the initial condition and the influence of the forcing functions? Can we account easily for non-homogeneous boundary conditions? This and more in the next exciting action-packed episode, I guess. Section 9.3, Green's functions for boundary value problems for ODEs. Oh, okay, so this I went through with you guys the other day. We basically came to the understanding that the Green's function had to do with we could find it from looking at the source being the direct delta function.
Okay. So just the pulse, basically.
Yeah, let's see here. Was Jess not here when we did that? I think you might have been sick on that day.
Yeah, that's what we did before we solved the...
That was the day you were sick. So if you watch the last 10 minutes of that, we stumbled into the idea that ties together with what we did at the start of today in terms of it was a comment about the Green's function for an ODE. Mm-hmm. I'll try to assign you guys a problem from that section so that you can internalize that, because I think you're interested in that. Okay. It's also there is some kind of connection between the direct delta function and the Green's functions that we would like to kind of get our paws on eventually. Let's see here. In fact, section 9.3.4 is the direct delta function. Its relationship to Green's functions. Woohoo!
I mean, that's
I should probably try to go through that another day and spend some time on that actually. Let's see here. Just a second, let me see if I can't get any more mileage out of today. Fredholm alternative and modified Green's functions. I'm not saying it's not interested, I'm looking for something that ties in with what we're doing at the moment. That's all. I think eventually, okay, so, this chapter is titled Time-Independent Green's Functions, by the way. So, you notice, well, but there seems to be a time dependence here, doesn't there?
Yeah. I mean, if T naught is also increasing, right?
Yeah.
It makes sense that they're both increasing at the same time, therefore the difference T minus T naught, whatever that value is actually fixed.
Well, there's definitely more to say about this chapter 9 stuff. Let me just skip ahead here for a bit. I need to do some reading before I try to dive into that. I knew we could do what we did today, and that no matter how much I study it, it's never going to be much shorter than what we did. And, well, I'm not sure. Maybe it wasn't a good use of our time to write these things down, but anyway. So chapter 10 is the Fourier transform stuff, which we'll eventually get back to. And then chapter 11, Haberman, of course, Green's functions for time-dependent problems. So there he does stuff like study the wave equation. Mm-hmm. All right, so I'm just trying to find a Green's function, see what the difference is. Come on. Would you write down the stupid function? Golly. Bowsers. I don't know. I do not entirely understand why he says time independent Green's functions here versus time dependent Green's functions in chapter 11. I mean, definitely the stuff in chapter 11 looks more complicated and different. I guess I'll put that on my list of things to try to understand. And man, there's just direct, it's all very, it's very direct delta E over here, Jess. You'll be very happy. There's lots of deltas floating about here and there and everywhere. Huh. Sum from minus infinity to infinity. Well, that's a lot. Cool.
Everything.
All right. Well, anyway, thanks for your patience. We will continue, of course, to...
I mean, technically it's no larger than 0 to infinity.
Right.